An aircraft carrier catapult can take an aircraft from a dead stop to roughly 165 miles per hour in under 2 seconds, on a flight deck moving across the ocean. From a distance, the launch looks instantaneous. Engines roar, a crew member drops, and the jet disappears over the bow. It is easy to imagine one signal, or one button, causes everything. But those 2 seconds are only the visible end of a much longer process. Before the aircraft moves, people, hardware, aircraft configuration, and a tailored launch setting must all agree. The crew follows a defined sequence in which each completed step makes the next step possible. Slow it down to reveal the catapult approach, the connection beneath the nose gear, and the final handoff from pilot to shooter to launch control. That sequence also separates two systems often blended together in popular explanations: the steam catapults used on Nimitz-class carriers, and the electromagnetic system installed on the Ford-class. Same mission, different path to the required energy. The basic problem is simple. Even an enormous aircraft carrier does not provide the takeoff run available at a land airport. Navy descriptions say the deck is too short for an aircraft to reach the necessary takeoff speed on engine thrust alone. The catapult adds the energy the limited deck run cannot provide. The catapult supplies the additional acceleration. But that does not turn the pilot into a passenger, and it does not turn the flight deck into an automated conveyor. The aircraft, the ship, and the deck crew still operate as one tightly coordinated system. The Navy has compared flight deck movement to choreography. Yellow shirt aircraft directors handle and maneuver aircraft, communicating with pilots and other deck personnel through precise hand signals. They translate the aircraft's next movement into a signal the pilot and nearby crew can recognize. Around them, other crew members secure aircraft, operate deck equipment, and support the catapult. Navy flight deck guidance assigns blue shirt personnel tasks that include chalking and chaining aircraft and operating support equipment, while green shirt personnel include members of the catapult crew. The colored jerseys make roles visible in an environment where engine noise can overwhelm ordinary conversation. Precision matters because the deck is crowded, loud, exposed, and active. The aircraft must arrive at the catapult correctly, and crew members must know when to move, when to stop, and when the space around the jet is clear. The choreography is a safety system as much as an efficient way to move aircraft. Behind the aircraft, the jet blast deflector rises before takeoff. Naval describes these as hydraulically controlled panels that divert hot exhaust, protecting the flight deck and aircraft waiting behind the launch area. Naval also treats the catapult, its control stations, and the jet blast deflectors as parts of the broader launching system. The launch is already larger than the track beneath the jet. The final approach is deliberate. The aircraft director guides the pilot forward in small, controlled movements. The tires are not merely following a painted line. The nose gear must meet the launch hardware in the right relationship. Official Navy imagery shows positioning as a coordinated interaction among director, pilot, and crew around the nose gear. The commander, Naval Air Force's launch guide, describes the front landing gear with 2 wheels and a launch arm, more commonly called the launch bar, at the front. During the precise roll-up, that launch bar begins in the raised position. At the correct point, the pilot lowers the launch bar. The published Navy guide depicts the catapult capturing it with 2 hooks at the shuttle, while official imagery shows sailors preparing and checking the connection. Because the work occurs low beneath the wheel, the launch bar, shuttle, and holdback must remain mechanically distinct. The shuttle is the moving connection to the catapult track. When the launch stroke begins, the shuttle travels forward and carries the aircraft with it through the launch bar. That is the forward pulling side of the system. The holdback serves the opposite purpose before the stroke. It restrains the aircraft while the launch is being prepared and while engine power comes up. In the Navy sequence, the holdback is attached before the pilot's control checks and engine run-up. The three elements have distinct jobs. The launch bar links the aircraft to the shuttle. The shuttle is the catapult's moving interface, and the holdback prevents forward movement before launch commitment. A tow bar is not a launch bar, and the holdback does not pull the aircraft forward. Forward force reaches the jet through the shuttle and launch bar connection only after launch commitment. The next misconception is that the catapult simply fires at maximum power. It does not. Official Navy material describes checks that account for the aircraft being launched and the conditions of that launch. Sending too little energy would not solve the short deck problem. Treating every aircraft as if it were identical would ignore the reason those checks exist. A Navy flight deck guide says the weightboard operator verifies gross weight with the aircrew as a final check. It also says different aircraft require different capacity selector settings based on weight. The launch team's number is checked with the aircrew before the shot proceeds. Naval says launch calculations use aircraft type, aircraft weight, wind speed, and other variables to determine the required energy level. Those words matter: type, weight, wind, and other variables. The public explanation shows the setting is conditional without pretending to publish an operational formula. The objective is a suitable setting, not the largest possible shove. That is why the setting is better understood as a tailored shot. The catapult must supply enough energy for the aircraft and current conditions while staying within the approved launch procedure for that aircraft. On deck, the center deck operator relays aircraft type, gross weight, side number, and capacity selector information to catapult control. The weightboard operator performs the final gross weight check with the aircrew. These distinct jobs show the launch is verified by a team, not entrusted to one dramatic control. Forget the movie-style power dial. Verified aircraft and condition information becomes the catapult setting for that launch. Once the aircraft is connected and the launch setting is established, the sequence becomes a chain of permission. The pilot conducts control checks, runs the engines up, and signals readiness to the catapult officer. The published sequence does not collapse these actions into one moment. The checks and engine run-up come before the pilot's salute. In the Navy's published sequence, that pilot signal is a salute. The salute does not fire the catapult. It tells the launch team that the pilot has reached the appropriate point in the cockpit procedure. The catapult officer, often called the shooter, still checks with the crew. Navy reporting describes the ready-to-launch signal toward the deck edge operator, touching the deck and pointing down the bow. The gesture is memorable. The crew checks before it are equally important. The deck edge operator then activates launch control. The familiar kneeling gesture is one link in a communication chain, not a theatrical motion, and not the only authorization. Around the aircraft, hand signals remain crisp because the environment leaves little room for ambiguity. Specialists must share the same state: aircraft positioned, connection checked, area clear, pilot ready, and catapult ready. That shared picture is distributed across the team. No single role completes the launch alone. If a required condition is not satisfied, moving faster does not make the launch safer. The launch advances only through defined roles, checks, and signals. Navy reporting on catapult crews returns to attention, maintenance, teamwork, and awareness of hazards around the aircraft. That is the hidden tension in the few seconds before the shot. The aircraft appears motionless, but engine power is up. The holdback is restraining it, and the catapult is prepared to deliver the calculated launch energy. Then the shooter makes the final visible signal. The deck edge control is activated. The launch is committed. At engagement, the holdback separates as designed, and the catapult drives the shuttle forward. Through the launch bar, the aircraft accelerates down the track. Restraint before commitment, separation at engagement, then forward movement with the shuttle stroke. This is the moment the eye struggles to follow. Navy reporting describes a catapult taking an aircraft from a dead stop to roughly 165 miles per hour in under 2 seconds. Exact launch speed and energy are not universal. They depend on the aircraft and conditions. The 165-mile-per-hour figure describes the system's scale, not a setting applied identically to every shot. By the end of the deck, the visible choreography is behind the aircraft. Launch bar, shuttle, holdback, control setting, cockpit checks, crew confirmations, and final signal have converged into one acceleration stroke. The speed of the result can hide how many dependencies were resolved first. What looks like an explosion of motion is the opposite of improvisation, the compressed result of every required decision made before the aircraft leaves the deck. Now, we need to separate the energy systems. On Nimitz-class carriers, the launch system uses steam catapults. Naval says the Navy has used steam to launch aircraft from carriers for more than 50 years. The steam system and deck hardware provide the additional acceleration the aircraft cannot obtain from the short deck run alone. Naval places catapults, control stations, and jet blast deflectors within the launcher system. Track, shuttle, aircraft connection, controls, and safety equipment therefore belong to one operational chain. Steam is not the entire story visible on deck. The aircraft still has to be positioned and connected. The launch setting still has to be verified. The pilot and crew still complete their checks and signals before the catapult is activated. On the Ford class, the Navy introduced the Electromagnetic Aircraft Launch System, or EMALS. Naval identifies it with USS Gerald R. Ford and future Ford-class carriers. EMALS has the same mission and function as a traditional steam catapult, but it uses entirely different technology. Naval describes EMALS as using stored kinetic energy and solid-state electrical power conversion. It also says the system allows a high degree of computer control, monitoring, and automation. In plain terms, the energy path changes from steam-driven machinery to an electrically controlled launch system. That does not mean the aircraft is launched by software alone. Human choreography, aircraft preparation, safety checks, and deck communication remain essential. The mission still ends with a prepared aircraft connected to a launch system and a crew verifying readiness. EMALS changes how launch energy is produced and controlled. It does not erase the launch team. Naval lists more accurate end speed control and smoother acceleration among EMALS's intended benefits. It also says the system is designed for a broader range of carrier air-wing aircraft, from lightweight unmanned aircraft to heavy strike fighters. Those intended benefits align with the central problem, delivering an appropriate result across aircraft with different requirements. Those are Naval's program claims, and they should be presented that way. A responsible comparison does not imply that every Ford-class launch is faster or that a steam launch is crude. The systems pursue the same operational result through different technology. Keep the difference straight. Nimitz-class carriers launch with steam. Ford-class carriers launch with EMALS. The aircraft may perform the same basic mission, but the energy delivery systems are not interchangeable. Return to the launch at full speed, and it still looks impossibly simple. A signal, a burst of motion, and an aircraft airborne over open water. But now the 2 seconds read differently. The launch began with aircraft handling and deck safety. It continued through mechanical connection, verified aircraft information, a tailored setting, cockpit checks, crew confirmations, and the handoff to launch control. None is as visually explosive as the shot, but each changes what the final 2 seconds are allowed to do. Steam or electromagnetic, the catapult is only one part of the system. The real achievement is the disciplined chain that makes enormous energy arrive at the correct aircraft, in the correct direction, at the correct moment. The technology is spectacular. The coordination is what makes it usable. If you want more films that take apart the hidden systems behind aviation, subscribe to The Empty Leg. The most dramatic moment is often only the final 2 seconds of a much larger story.